was to enable counting by age group instead of just by age. The machine ran at 400 cards per minute, but the actual throughput time depended on the frequency of totals, because printing a total took a time equivalent to 9 card feeds. One of the things that strikes me about it is that the functionality is remarkably simple, similar to the functionality of the machine that Herman Hollerith devised for the 1890s census in the USA. The flexible connections between card columns and counters are the same. The combination of counting and sorting is the same. There are 2 crucial differences really. The movement of the cards is automated and the results of counting are automatically printed. But the Hollerith ideas persisted for census work for quite a long time. I don't know how census analyses have been done since those days. Not more neatly than that, I would suggest. Next machine is the PCC, a program-controlled computer. You'll notice that the program hasn't yet lost its final ME. It certainly had a program by which it was controlled, but calling it a computer was perhaps going a bit far. It wasn't a full computer in the sense that the society understands, where the program is itself held in store and may be modified during running. But then, Power Samus was not aiming to achieve a completely general computer in the modern sense. What they wanted to create was a machine that could take its place in the work of a conventional punch card installation. Its predecessor, the EMP, the electronic multiplying punch, was limited to multiplying with a bit of cross-adding thrown in. By contrast, the PCC was much more flexible. I note that when Power Samus and the British Tabulating Machine Company merged to form ICT, and a common way of identifying both product ranges by type number was established, the PCC was given the numbers 556 and 557, which places it firmly in the same category as the BTM calculators, the 542, 550 and treble 5. To program one of those calculators, you were given a fixed number of program steps, and at each step you had to plug the function to be performed, the source position of 1 or 2 operands, the paths by which they were to be accessed, the destination of the result, and the path it was to follow, plus sundry niceties. It could be quite challenging to get all of these right. By contrast, a program for the PCC was much like a program in a proper computer. Admittedly, the number of program steps was still limited, but each step was much more simple. Just choose the right function code and specify the operands. Physically, the PCC was quite a big beast. 12 feet long, 6 feet 4 inches tall, and nearly 3 feet from side to side. And it weighed a heck of a lot. The last time I saw one was about 2 years ago, when John and I went down to Rawton and saw one languishing in one of the hangars there. It was a machine which had run accounting systems for many years for Swindon Council, but now it had been split down the middle, mounted on a couple of pallets, and this end was switched the wrong way around, so it didn't look as though it fitted with the other part of the machine. It was a sorry sight. Since this was a punch card machine, I'll start with the detail of its workings with the card track. The magazine into which the input cards were placed was at the right-hand end, immediately underneath the operator's control panel, and the receiving hopper was halfway along the side. The cards were fed through two successive reading units, and there's a punch unit and another sensing unit there. Each card was read twice, and the results of these two readings were compared. And if there was any discrepancy between them, the card was rejected. It's not possible now to say why the designers included this feature, but my guess is that it's a symptom of a typically power-samous distrust of all this electricity stuff. A quote down the bottom of the brochure says, "Reading and punching, mechanical, therefore positive." The data from a successfully read card was then distributed into the store through an application-specific mechanism similar in principle to the connection box in a Powers tabulator. And while the program was being obeyed, the card moved forward to the punching station, and when the program was complete, the results were punched into it. It then passed to another reading station, where the results actually punched into the card were compared with the results computed by the program. A card which passed this test was ejected into the receiver. Any card which failed either test, after the second reading, or reading after punching, was inverted before being put into the receiver. There's the story of the two inexperienced operators left overnight to put a long run through the PCC, who decided that these inverted cards looked a bit untidy. So they turned them all right way up. When the supervisor came in the next morning, "What? No errors?" was her first remark. Better forget what she said next. The store, for data only, was on a magnetic drum and was arranged in 6 tracks, 1 input, 1 output, and 4 main storage. Each track could hold 40 words, and each word could contain 16 digits in either decimal or sterling form. In addition, there were 6 fast access stores interposed between the main drum and the arithmetic unit, but they were also somehow incorporated into the drum. I can't remember how this was done, and the documentation rather skates over it without giving any detail. The literature of the beast also says rather snippily, "The PCC does not use the binary scale of notation, but performs arithmetic directly in the familiar decimal and sterling scales. This is one reason for its high operating speed." There's its drum. Looks, I think, like pretty well all drums look. And now we come to the unique feature of the PCC, the method of inputting the program to the beast. The program could consist of up to 160 steps, and they were input on 4 program boards. And this is one of them. Each program board could hold 40 steps, each step being represented by a transverse row of holes. And into the appropriate holes were fixed rivets, which, when the program unit holding the board was closed, provided an electrical connection between the 2 sides of the board. Hence the cynical remark of one field engineer, "These boards were riveted by a bleeding programmer. Listen to them rattling about, they're loose." And there was the installation where 2 sets of data could be processed by almost the same program. The second set required only 1 change in only 1 bit of only 1 program step. So rather than riveting up a second set of boards, I think it was Philip Sugden found it worked at the halfway stage if he slipped a minute bit of sellotape onto the one distinguishing rivet. Yeah. Here's the first coding sheet of a program for stores accounting and a control. One coding sheet is very much like another, but this shows that it was written in March 1957, that the programmer was Gordon Rearcrew, who was my team leader when I myself became a programmer, and that it was approved by Peter Ellis. And Peter went on to become a senior director of ICL. When I joined the company, Powers had on the sales side a computer department with 3 members: Peter Ellis, Gordon Rearcrew, and John Lilly. He was a statistician known as Lilly the Figures to distinguish him from the other John Lilly in the company. And here's a picture of a very young Peter Ellis instructing a programming class. I used to know who those other 2 were, I can't remember now. But I vividly remember the occasion when 2 PCCs were delivered to an office of British Rail built alongside a convenient piece of railway siding in Crewe. Bill Lumbers was the salesman, Gwen Steele was his support, and I was along as a spare operator. The gleaming new computer room was on one side of the building, and the other half of the same floor was occupied by clerks sitting on high stools in front of desks whose sloping tops were covered in green leather. They looked as though they must have been there since the 19th century. Now, the desks, I mean, not necessarily for clerks. Anyway, the first machine was lifted into the building with great care by a crane hired for the purpose by ICT. The British Rail people watched this process, and when the second machine was delivered a week later, they said, no need for us to provide a crane. They now understood what was required, and one of their own breakdown cranes could do the job perfectly adequately. So they whisked the second PCC over the roof, slung it in through the window, and dropped it the last 2 inches. The annoying thing was that their machine worked almost from the first switch on, while ours took a fortnight to commission. Next, the FCC. Crafty name chosen to stand for both 40-column computer and ferrite core computer. But given the type number 558, which again made it appear to belong in the family of calculators, whereas it was actually more nearly a full computer in the sense that we use the term. Since it was designed to provide computing capability for 40-column users who tended to be small businesses and very cost conscious, the machine was kept as simple as it could be, which actually meant that part of the job of programming an application was more complicated than it might otherwise have been. The basic machine had one cabinet containing the processor and another containing a card reader punch. The processor had ferrite core storage for 128 words of program and 32 words of data storage. These could be increased to 256 words of program and 64 words of data. And another option was to add a second card reader punch. The cards were fed sideways, column 40 leading, through a photoelectric reading station to a waiting position. The direction of that travel then changed, and the cards were fed with a 10 edge leading through the punch station, which was a conventional Powers type punching unit. The block comes down and all holes are punched simultaneously. Throughput was 540 cards a minute if no punching was done. If every card was punched, that rate dropped to 135 per minute. There were 2 receivers, which is what the girl was looking at. They could be filled either sequentially, or the program could optionally direct selected cards to receiver 2. Internally, the data store was divided into 2 banks, imaginatively called A and B. Each word consisted of 10 data digits plus sign, and B0, the first word of the B store, functioned as an input buffer. There were also 8 words of C store as an output buffer, into which data to be punched was placed by the program. Data was held in decimal or sterling form, so again, there was no inward conversion to binary and no outward conversion from binary. But the program itself was held in binary form. The instruction format had 5 bits for the function code, 5 for an address in the A store, 5 for an address in the B store, and a single bit in the AB suffix. So an add instruction, for example, would add a number in the specified A store and a number in the specified B store, and place the result in either the A address or the B address, depending on the AB suffix. There were only 20 instructions in the machine's repertoire. Add, subtract, in both decimal and sterling, copy, halve, shift, modify, conditional and unconditional jumps, punch, send the card to stacker 2, and so on. There were no built-in multiply or divide instructions, but these functions were provided by subroutines which came with the machine. The first subroutine was in fact a complete program. Its function was to convert the instructions of a user program, which the programmer punched in clear into the program cards, into binary. So here's what the programmer has punched. Function code, A address, B address, and AB suffix. And the binary form of instruction was punched by the program into the same cards, but there was a quirky feature in this punching. If the binary form of an instruction contained a row of successive ones, it was felt that the card might be weakened and it might misfeed, and therefore the actual binary punching was arranged diagonally, like so. Crafty. Once the program cards had been converted in this way, then obviously they could be retained. And in the normal procedure for a run, the program pack would be read first, followed by the relevant data cards. There was also a third form of input to a program in the form of a simple plug board. I wonder where they got that idea from. Its function was to define the layout of the data cards, explain the meanings of any control holes, and so on. The fields which would form factors for the program's calculations would normally be at the right-hand end of the card. So as the card was read, starting from column 40, characters would be read from successive columns and into B0, the input buffer, until the plug board signaled end of field. At that point, the first instruction of the program would be obeyed. It would always be a transfer from B0 into an address in the A store. This would be repeated for successive fields, each in turn being transferred into the A store until the plug board signaled end of sensing, and this would allow control to pass to the rest of the program. Here's the first page of an FCC program for a costing application. You can perhaps see that the first 6 instructions are indeed transfers from B0 to successive addresses in the A store. The other thing to note is that this program was written by Gwen Steele and checked by Jill Goodrum, who married Tony. I can visualise him clearly, but can't remember his surname.
Clark.
Clark, of course, yes, a nice couple. The subroutine repertoire was reasonably comprehensive. Multiplication and division, of course, various conversions, farthings to decimals, hours and minutes to hours and decimals, and vice versa, quantities in dozens and singles, square root, graduated pension scheme, PAYE, normal cases only, weekly tax routine, monthly tax routine, and coin analysis, all functions which are likely to occur in conventional punch card application systems. So here's a block of data store, looking, I suspect, very much like any other matrix of ferrite cores. program store likewise, and the arithmetic unit neatly mounted in a door of the processor. It always seemed to me that, as a layman, that the engineering of the FCC was particularly neat. This shows in the card reader punch, the hopper, the photoelectric reading station here, the waiting station here, and then the punch unit further up. As a programmer, I enjoyed the little bit of work I did on the FCC and remember it with affection as a nice machine to operate, but it only had a short life. Despite efforts to keep its cost down to the minimum, I suspect it was just too expensive for the average 40-column user.
Can I add a supplementary on the FCC?
Yeah?
I joined Power Samus 2 weeks after Hamish, so I'm a new boy. And I didn't actually have anything to do with the FCC, but I understood that the logic was also ferrite core, as well as the storage on it, and that it suffered from a malaise that made it difficult to maintain because at that time it hadn't been discovered that any logic stage must contain amplification and produce an output at standard level. And the FCC contained ferrite logic that didn't maintain this principle, that came in initially on Orion 2, I believe, at the instigation of Gordon Scarrett, whom I worked for later. So it was slightly unreliable to maintain, though that didn't spoil it for the programmers, I'm sure.
Thanks, Jim. Yeah, that's absolutely the right reaction. A universal groan. Yeah.
Sorry.
This mighty beast was supposed to be the tabulator, to end all tabulating. But I believe the only end it actually achieved, really, was the end of Power Samus. It was launched, perhaps prematurely, in 1956, and I've always understood that the excessive expenditure which its full development required was more than the company could afford, so that the merger with BGM in 1958-59 was more of a takeover. I spent part of October in 1958 running several Samastronics as an operator on the testing floor at the Aurelia Road factory in Croydon, in preparation for demonstrating one at the major electronic computer exhibition at Olympia in November of that year. The taller section at the right contained the card track, the columnar decoders which interpreted the content of a card column into electronic form, the arithmetic units, and the control logic which hung it all together. The card track was fairly conventional. There were two sensing stations, the first to control totaling, and the second to read the data required for adding and printing. 3 levels of totals could be taken. I think it must have been about 1910 when Powers produced the second or third version of its tabulator, that the total controlling mechanism was added, and at that stage it was fairly called an attachment. 50 years later, after generations of tabulators with this facility provided as standard, it was still called the ATA, the automatic totaling attachment. Powers' nomenclature could be pretty weird. Adjustable stop basket combs, anybody? Independent sector designating devices, and so on. Cards were fed through the Samastronic at 300 per minute. There were 2 receiving stackers which operated alternately. When the first was full, the flow switched to the second, and this certainly made it easier for the operator to empty them without interrupting the flow of cards. On the back, somewhere in there were 7 adding-subtracting units in the basic machine, and they could be specified as having either 10 or 13 digits. And if that wasn't enough, additional arithmetic units could be specified, but they'd had to be housed in a separate cabinet. And I haven't found out if anybody ever actually required them. Most of the elements shown here are the column decoders, which turn the signals read from card columns into the form needed for internal working. They always seem to be surprisingly large, and I think that must have been because the internal technology of the decoders was based on relays, which must have been approaching the end of their life as a generally accepted technology. I've no evidence for this, but I think they would have been chosen because there was something more familiar and comfortable to the power summers mind about a component which had a visible bit of physical movement to it. And now we come to the glory bit, the printing mechanism. The printing head is shown here in the raised position. The essential heart of this was a bar which oscillated laterally across the print bed at the same time as the paper was moving steadily forward. The bar carried 140 styli, one for each possible character position. And the combined effect of the two movements was that each stylus executed a zigzag trace across one character width of the paper. There could be a single carriage, as shown here, enabling printing to be generated at the full 14-inch width, but there was also an option to have two independent print carriages side by side. This could be used, for example, to print full invoices on one side and invoice summary lines on the other. It could print on multi-part paper with interleaved carbons, handling original and one or two carbon copies, or instead of interleaving, there was an option of a carbon creep mechanism which economized on the use of carbon at the expense of increased mechanical complexity. Line spacing could be set to either 6 or 8 lines to the inch, and this was easily managed by varying the speed at which the paper was moving. There was also a facility to speed up the paper movement for a particular line, producing elongated characters for emphasis. Each stylus was activated by its own solenoid, which lived up in the head there. So a printed character was made up of a series of dots created at the appropriate point on the zigzag trace of the stylus. The impulses to the solenoids were generated by character discs, non-conducting material with metal inserts at appropriate points round the rim, energized from a common source. And they were read by brushes. Brush sensing in a powers machine, whatever next? Printing operated at 300 lines per minute, or 5 lines per second. The oscillating bar executed 22 passes across the character space for each line, 15 passes used to generate the character, and 7 passes for the interline space. I work out from that the time available for a solenoid to generate a dot and recover ready for the next dot was about 1.8 milliseconds, which sounds pretty challenging to me. A little subtlety. The zigzag trace meant that any horizontal lines in a character, a capital B for example, were not exactly horizontal, but it was found psychologically preferable to have such lines generated on the path which goes upwards from left to right. The standard repertoire allowed the generation of 50 different characters. Standard set comprised A to Z, 0 to 9, quarter, half, 3/4, that's for dealing with farthings, 10 pence, 11 pence, percent, plus, minus, pound sign, open and close bracket, ampersand, and asterisk. The use of character disks meant that it was easy to generate non-standard characters, such as the accented e's and o's in the Swedish language. At many places around the machine, there were slots to accept electronic connection units, ECUs, which linked the various functions of the machine together in an application-specific manner. This was explained as maximizing the flexibility of the machine, but a cynic would say that the designers weren't sure how to link the units together, so left it for the user to decide. Each ECU could be either plugged up by the user or bought pre-wired from the factory. Other components. Another rather nifty feature, tucked away somewhere in the back there, was the phrase printing facility. A phrase of up to 32 characters could be generated, it could be set up in a special store, and then its printing could be triggered by a control hole in the appropriate passing card. There was supposed to be a dedicated summary card punch designed to work at the same speed as the tabulator. I never saw one, and I don't know if it ever actually saw the light of day. While we were running Samstronics under test at Aurelia Road, the new chairman of ICT came out, Sir Cecil Weir, and the testing floor was a fairly open space run by a formidable woman who had a cabin up in one corner and could talk to the operators from the balcony outside it. And she had a good North Atlantic voice. There was no difficulty about being heard at the far end of the floor. And during the inspection day, charge hand came up to her and said, "May, tone it down a bit, Sir Cecil's coming round." And at full volume she said, "Sir Cecil, ho!" And at that point, a dapper little silver-haired gentleman emerged from around a recent nearby machine and said, "We're, madam." As I said earlier, we proudly demonstrated this marvellous device at Olympia in November 1958, expecting the rest of the world to be staggered by its speed of printing. So it was bad luck that at the same event, Rank were able to demonstrate their mighty Xeronic printer, the first public appearance in the UK with the principle of xerographic printing. Although an experimental prototype, it was much faster than our machine, 1,500 lines per minute, and they expected it to crank up to 3,000 lines per minute. But at least ours didn't catch fire quite. So the Samstronic was never the commercial success the company had hoped for. I believe it suffered from terrible reliability problems. There was a subsidiary sales line making the printing mechanism on its own available as a peripheral for other people's computers, but that didn't do well either. I've heard of a normally phlegmatic Swedish customer getting apoplectic with rage over it, and most people who came into contact with it have their own horror stories. R.I.P. Now then, here's the thing. This is probably the most interesting of the machines I'm covering today, because it was unlike anything else in the punch card world. It got the name from Mr. E.T. or E.C. McClure, about whom, apart from his name, very little is known. I believe he may have been Australian, but can't be sure, and it's not clear whether he worked for Power Samus at the factory in Aurelia Road, or whether he sold his invention to the company before lapsing into obscurity. What we do know is that he built a prototype of his multiplier in 1934, and that Power Samus brought out a production version in 1938. But to set it in context, this is the academic bit. Leibniz in the late 1600s is generally credited with inventing the method of multiplication involving successive addition and shifting of the multiplicand, which probably still goes on today below the surface of a lot of the multiplications carried out. It's simple and effective, but the number of cycles it requires depends on the value of the digits of the multiplier, so it can be expensive in machine time. Therefore, over the centuries, many people have tried to devise a method of more direct multiplication. Here are just a few of them. Edmund Barber of Boston, Mass. filed patents in 1872 for a multiplier with a sliding carriage, multiple pinions, and mutilated gear racks, the arrangement of the teeth serving as multiples of the digit they represented. He subsequently patented an associated printing mechanism. Ramon Varela was a Spaniard who moved via Cuba to New York just after the American Civil War. His motivation seems to have been national pride. Spanish brains ought to be able to invent things that would restore Spain's former national superiority. So in 1878 he produced a direct multiplier based on a 10-sided cylinder, each side having a column of holes with 10 different diameters. The notes say that it worked rather like a Jacquard loom. Léon Bolle, a very versatile Frenchman, devised several interesting machines. The direct multiplier used a number of bars with attached pins with various lengths, somewhat like a mechanical representation of Napier's bones. In operation, the pins come into contact with gear strips which move by different amounts depending on the heights of the pins. In 1992, he demonstrated a machine calculating automatically the square root of an 18-digit number in about 30 seconds. He then took to motor cars in a big way and is famous as having founded the Le Mans 24-hour race. Otto Steiger patented his millionaire machine in 1892. It used a mechanical representation of the multiplication table to form partial products. These were passed through a transmitting mechanism to a combining and registering mechanism to display the results to the operator. A trained operator was able to multiply two 8-digit numbers in about 7 seconds. Unlike the preceding machines, this one went on to become commercial, and although very expensive, more costly than a top-range motor car at the time, it remained in production until 1935. So, from what we've seen, the McClure multiplying punch was not unique, except in one aspect. It worked in sterling. How complicated we used to make things for ourselves. This is not perhaps the most informative picture, but it does at least prove that the thing did exist. And it actually looks not unlike the later EMP, the electronic multiplying punch, which emerged to perform the same functions in the 1950s. I'm not going to go into any detail on this. These are just some indications of what the documentation said the beast could perform, and who am I to argue with that? What the machine was trying to achieve was a form of mechanical lookup from a table showing the results of every possible combination of digits from the multiplier and multiplicand. Some say this way of tabulating the results of all possible multiplications goes back to Pythagoras. Maybe so, but at least Pythagoras didn't do the same job for sterling multiplications, so shown on the right here. The crucial step was to convert each line of a product table into a stepped profile with the height of each step corresponding to the numerical value. I apologise for the quality of this and some of the following pictures. The documentation of the machine in the Science Museum Library at Rawton is not a printed original, but a rather tired copy, and the image hasn't been improved by the process of getting it into this presentation. The product shows the profile for the ×7 line, with the pence products on the left and decimal on the right. I'm not sure whether the actual machine ever had compound plates on the lines of this diagram. But here's a picture of an actual profile plate, again from the ×7 line. I photographed this one in the museum store in Blythe House. You can hopefully see that each product has a 2-digit form, the left hand digit representing shillings, the right hand one pence. So here's ×1 is 0.7, ×2 is 14 pence, that's 1 shilling and 2p. Remember that? I particularly apologise for the quality of this slide. If it was clearer, we could spend ages going through it in detail. As it is, its fogginess rather matches my understanding of what's going on. We're looking at the multiplier end of the calculating head. The multiplicand would be behind this. The information comes up from the card through a connection box, which performs very much the same function as it would in a tabulator, and sets up stops in a stop basket. While the multiplicand is set up in a similar stop basket behind. A control is also set up at that stage to say how many digits there are in the multiplier, and therefore how many multiplying cycles will be required. On a multiplying cycle, the appropriate multiplier feeler bar moves forward until it meets a stop in the stop basket. And here's the multiplier feeler bar. It has moved forward, and in fact it's encountered the 9 stop raised in the stop basket, which has resulted in raising the appropriate profile plate, the 9 plate. And this actually has got both decimal and sterling products in the same profile. You can tell that's decimal because of the nice way the 9 multiples make that neat pattern. The multiplicand feeler bars similarly move forward until they are arrested by the raised stops in the multiplicand stop basket. They then send fingers down to sense the relevant parts of the profile plate. And this vertical movement is transferred via the result plates across to the vertical results bar, where they are then wound on to the accumulator wheels. The multiplicand is also moved by Bowden cables, which mercifully are not shown here, to the 10 times unit. The stops in the multiplicand basket are cleared, and on the next cycle, the multiplicand feeler bars move forward to sense the stops in the 10 times unit rather than in the original multiplicand unit. So that copes with the shifting of the multiplicand part of the process. When all the multiplying cycles have been completed, the finished product is read off the accumulator wheels and passed to the punch unit, where they go into the card, which is meantime passed on from the reading station to the punching station. And at the same time as punching is going on, the next card is being read and the factors being set up. This was the justification of the whole machine. the value of the multiplier digits doesn't matter. The only thing that counts is how many multiplier digits there are. Got this wrong way around. Going back, this shows the multiplicand feeler bars, and they send feelers down which sense where these transverse bars are. The transverse bars fit into the slots of the profile plate, effectively setting that profile across the whole width of the multiplicand. So, and the movement of the feelers determines where the stud on the vertical bar meets the stepped profile in the result plate. And that's the key to the business of carrying, because each product read off the product profile has 2 digits, one to be registered in the relevant digit and one to be added to the digit on its left. There's a subtlety by which each unit is able to nudge the result plate of its neighbour on the left, so that what gets added to the accumulator wheels is the arithmetically correct combination of figures. For example, multiplying 25 by 5, the Unix product is 25, the tens product is 10. And by the nudge, the 2 is added into the tens position, giving the correct product of 1, 2, 5. This splendid piece of kit, which McClure used to demonstrate the principles of his invention, was presented to the museum in 1938 and currently lives in Blythe House. As far as I can make out, it differs a great deal from the production version of the machine. There's a keyboard with which to enter the multiplicand. When that has been registered, the same keyboard can be used to enter a digit of the multiplicand, and there's a hand wheel to move it through the process of multiplication. But of course, in the museum's eyes, it's not a machine, it's an object. So even with white gloves on, you're not allowed to touch the keyboard, let alone turn the hand wheel. Pity. One final point, there's a letter dated 6th of October 1957 from A.R.W. Hill, manager of the Local Government and Public Utilities Department of Power Samus accounting machines, to the Science Museum, and it says, "I remember that you have some of the original McClure multiplying mechanism in the gallery. In this connection, you may be interested to know that the Southeastern Electricity Board at Hollyfield Road, Surbiton, has for disposal now one of the early Power Samus machines constructed on this principle. As an accounting machine, it now has no value, and I fondly imagine the Electricity Board would be happy to donate it to the museum if you were interested. The machine, of course, has special interest, since it is a specimen of a very small range of machines built to operate on a table lookup principle, and which of course has now been superseded by electronic calculation and will never again be built." But I don't believe the museum took up the offer, and so the McClure multiplying punch is probably now as dead as the dodo. So, the ingenuity may have been displaced, but wasn't it fun? One sort of postscript. May I just check how many people here worked for ICL? On stage, hands up please. Majority. Well, what I'm going to cover last will be familiar to you, but it was a well-kept company secret I think can now be exposed, and it's worth going through it for the benefit of our colleagues. Many of you will remember Neil MacPhail's excellent talk on the development of disk storage technology. Well, in the mid-1970s, when the clever people in Stevenage were developing things like CAFs and the file correlation unit, taking Neil MacPhail's ideas one stage further, the team produced the galactic storage device. And the 1900 were doing very well at this time. The principle of this was, if you look at the history of storage, first generation mag tape, essentially linear, one-dimensional. Disks, clearly two-dimensional. The natural progress from that is into 3 dimensions, as for example we're seeing at the moment with television. So the galactic storage device has at its core storage elements on which tracks of the data could be written in 2 senses, on either polar tracks or equatorial tracks. And the globes could be made to either spin or twist, according to which direction we were using. The storage elements were held in a planetary transport system which had, caused by geometry, obviously the outer planets were larger than the inner planets, and there were 2 orbits around the reading station. And a planetary transport unit of that sort could be joined by 3 others, and with 2 reading stations. And the appropriate planetary transport system was brought into position by the reading unit by the process known as precession. Well, you'll be familiar with precession of the equinoxes, for example. But you will, of course, remember from the Just So stories that in the end there was nothing left of the equinoxes because the precession had proceeded according to precedent. The balls were read on air currents in the either twist or spin configuration. And the housekeeping software that went with this, the galactic housekeeping software, sensible name, GASH, this is an example of some of the... are those legible?
Yeah.
Some of the controls. And the software could communicate with the outside world, obviously by printing messages on the console typewriter, and these are some of the messages that could emerge. And now you, of course, are far too fast. But it used to be a game in the training school to see, after a morning's lecture on discs, to see how far you could get with this before the penny dropped. And the champion, I think, was a fellow, his former colleague, splendid fellow called Dick Jukes. And his greatest triumph was when at the end of the session, the customer came up to him and said he needed to get in touch with the salesman straight away because he wanted his company to be the first in South Africa to have this splendid machine installed. There was just one problem. All the operators in his installation were ladies. And could something be done about the error messages because they might find Okay. That's wasted enough of your time. Thank you all very much.
Thank you very much, Hamish. Has anybody got comments or questions?
One.
At the back.
Oh, I'm sorry. Sorry, the man with his hand up. Is it? Yeah. Does that work?
Yes.
I'll try to. all of this, a lot of this is too horribly familiar. I will contain myself. Just going back to the Sanastronic, I remember a frustrated sales manager saying that if you're going to design and market something that doesn't work, you might as well have a good spec. He felt the Sanastronic satisfied that condition. On a more serious note, I mean, not only did it cost a fantastic amount to try and get working, but having announced it, I understand it virtually killed the sales of the conventional tabs, not only for Power Samus, but also for some of the other companies.
Yeah.
But the most drastic effect was on Power Samus because it affected their cash flow.
Yeah.
So there was even less cash to do the development or get it working at all. Just on subject of reliability, around about 1963, I was looking after Southwestern Gas Board that had 4 of these machines. And at any one time, one was permanently cannibalised, one was being repaired, one was waiting to be repaired, and if the customer was exceedingly lucky, one might be working. I'll come back to PCCs later, I'll get somebody else to go.
Is it going? Yeah. Hamish mentioned about the fast store, how he didn't understand how it worked, all the software that was quite ingenious in a way, because a fast store was effectively an area of the drum between 2 fixed heads, or in fact 3. And you wrote the digits on the right head. They took a finite time, which is equivalent to a number of clock track changes, until it got to the other end, and then it was read back again. So a fast store would hold, in fact, 4 of these in parallel, because, as you said, it wasn't working decimal. 4 of these in parallel would be holding the full word, and in particular, effectively rotating on the drum. And you say, what happens next? Well, the next thing is you had a solid magnet just beyond the reed head that cleared it all off and allowed the bit of the drum to move around and do a new job on the next set of fast stores. So you went even slightly further than that, because I think perhaps a couple of them, perhaps the program I still remember, were actually one bit less, with a flip-flop on the end to put the last bit back in. But if you wanted to shift, effectively multiply, the basis for multiply, then you cut out the last flip-flop and use one less bit on all 4 in parallel to shift it, and it costs a factor of 10. Binary. It's moving, it's multiplying, if you like, or the basis of which you can multiply by 10. Here ends the lesson.
Very good.
There was a gentleman at the back.
Firstly, a question. You mentioned Bowden cables right at the start. Do I take it those were entirely mechanical, like bicycle brakes, that the sensor had dropped a pin and that was transmitted through the wire to push the counter mechanically?
Yes.
So it wasn't an electrical connection.
Yeah.
The second point, it just struck me as very interesting the way that printer worked, of doing the zigzag printing. That technique emerged 10, 20 years later in the Mannesmann Tally printer, which had just 2 moving parts, the rotating drum and a comb oscillating from side to side very rapidly, and the lower solenoids which pulled the comb teeth backwards and let them ping forwards to make an intersecting point. So the technology wasn't completely wasted, it did turn up again.
Thank you.
Can I pick up a quick answer on the Bowden cables? Power Samus didn't actually use them like you'd use them on a bicycle. The centre was under compression. And this meant that you could re-establish a level by putting a stop on the receiving end, and the sending end moved slightly more than the receiving end allowed, allowing slight expansion in the cable. So Power's got the re-establishment of level right on their Bowden cables, but as I said earlier, slightly wrong in the logic of the FCC.
Thank you, Jim.
Well, thank you for your contributions, and thank you very much, Hamish. And just to remind you, or tell you if you don't know, that Hamish has 2 collections of stories about the early UK computer industry, and you can find them by browsing online. You can either get it to a link through a link from the CCS website where the talk is announced, or you can go to the Fujitsu, as it now is, site, pensioners topic stories, and you will get to it that way, and that will be well worth doing. So thank you very much indeed, Hamish. And do make a note in your diary for our next presentation on the 16th of February, which is called Bloodhound on My Trail, Building Process Control Computers, and is about the Ferranti Argus, which was among the first computers worldwide used for direct digital control. And this presentation will discuss how the computer was invented and how it was developed in military and civilian contexts by small communities of practice, and that it was a key transition from analog to digital control in manufacturing industry and hardware in the early 1960s. And the speaker is Jonathan Aylan from Manchester Institute of Innovation Research, Manchester Business School at the University of Manchester. And also, for future reference, just note the 16th of March, where we have a presentation on Turing and his contemporaries by our authors of the new book, which will be out by then.
Will there be copies available from the meeting?
You mean the 15th?
We believe there will be a 17th.
We hope so.
Yes.